Okay, so let's see, that's recording. Yeah. All right, so let's get started. So this class is thermodynamics. Which one? ES305. Thermodynamics. Okay, so here the important part is to realize that thermodynamics is based off two words. One, which is dynamics, so you have that class. So what would be the equation that defines dynamics? The equation defining dynamics, the main equation will be Newton's second law, which is summation of forces equals to ma, okay? So the fundamental equation that will be used in thermodynamics will be this one, summation of forces equals to ma. And from here, we're gonna derive equations that will be called principles, okay? The first term is thermal. Thermal is related to temperature. More specifically, it's gonna be related to heat, okay? So basically, and heat generally in thermodynamics is defined with the letter Q. So basically, a definition of thermodynamics is to study the motion of the heat, no? Dynamics, you study the motion, and thermal is the heat. So let's say, to study the motion of the heat, and the main idea of studying the motion of the heat is to do what? Think about the steam machines, no? The heat, you transform the heat, you boil water, the ball is gonna move a piston, the piston is gonna move an axle, the axle can move whatever you want, okay? So that was the main reason of the beginning of people starting to develop the different equation and the theory of thermodynamics. All right, so here I want to say that the main purpose of the development of thermodynamics was done during the 17th and 18th century, and basically the main problem in those years was what? I mean, cars were not here. Steam machines, they were brand new, no? If you think about it. So they were not really using that one. But there was something that everybody had to use in their homes, and think more about Europe than the United States. Even the United States was the same thing. They generally heated their home with coal, okay? Where you live outside the big cities, you will use wood, no? Okay? But the coal comes from what? You need to go and mine it. So what is the major problem in any type of mine? When you dig underwater, when you dig underground is water, all right? If you dig, you're gonna have water accumulation. So in all those mines, if you think about England, Ireland, Scotland, north of France, Belgium, Germany, and so on, all the time people were going in the coal mines, the main issue was water. So they needed to remove the water from the bottom of the mine. So at the beginning, what they were doing, they would just had buckets and they would just attach, you know, like a horse or a mule, no? And it would be going up, up, and up. So that was a major issue. So that was the main concern in those years about the engineering, okay? So all the first patent that you see about engines, the main functions was not at all like cars or locomotive, was really to solve the problem of the water going into the mine, okay? So in that respect, you will see the years would be probably 17th, 18th century. And basically the first one were in, so let's say here, were coal mining, water issues, so they needed to remove the water. Okay, and the other one, which is not maybe that important, but it's really also the beginning of the idea of the engine, is that they used to have a lot of debris from animals that they were killing to eat. And one way they were eliminating all the bones and everything was just to cook them, okay? They used to put them in what they call pressure cooks, okay? But they will not understand the principle of the pressure cooks. So you see, this is pretty old. All right, so the main foundations were done around 1656. You're probably going to remember this name. One is Boyle, probably have here this name in chemistry. And the other one, if you had solids, which I think you did, there's something called Hooke's law, no, in solids. All right, it's the same guy, but it's not the same principle. So really the story here is that Boyle, I think Hooke's was one apprentice of Boyle, okay? And they kind of both came up with the equation that relates the pressure and the volume. They say that this product of two quantities, pressure and volume, is constant. Okay. Later on, based on that, this one, a French guy called Guy Lussac, developed what is known as the ideal gas relation, meaning that PV equal nRT. And there we go. So camera up. All right. All right. So hopefully I should be able to link the previous video to this one. All right. So here we go. So they developed the Guy Lussac. So this is the relation for the ideal gas relation. Okay. Now, what else can I give you here? Yeah. Okay. I'm going to do very quick from now on. Then really the first engine was developed by Thomas Savery. Is really the first one that did the first engine. So all of these ones are based on steam engines. And then probably you remember that you might know this name. The first functional name, the first functional engine was developed by Newcomen. And he's really the first one that got the first real good patent. So this is really the first functional engine. Okay, and obviously, then there's one that Watt also did an engine, and this is the same guy that defined the units of watts. Okay. So this is the origin of the motivation. The guys that work on the engines, they didn't know much about the theory, but they were making the engine works and they were taking patents, okay? But they kind of had a good intuition, but they were not able to put numbers or to say my engine is that efficient or anything, no? They were just able to say this engine works or doesn't work, okay? So the first real, if you want calculations, were done by Carnot, which was a French engineer around 1824, okay? That based what is called as the Carnot principles, okay? And this guy is really, if you want, the father of thermodynamics. Okay? So basically, the main first problem was what? When people were solving thermodynamics. They all knew that what was the main goal? Was to try to obtain from heat they wanted to obtain work. Okay? All right? So that was the main thing. So the first part of the class would be based on, okay, how much work can you get out of a certain amount of heat? Okay? And this, if you want, will lead us to what will be known as the first principle or what they call in the textbook first law, but I like to call it principle of thermodynamics. What is the difference between a law and a principle? So for me, a law, for me, is something you cannot prove or derive. So Newton's law is summation of forces equals to 0 for statics, summation of forces equal to ma for dynamics, no? It's a given equation. You cannot derive it, all right? A principle is something that is derived from a law, okay? And you will see that the first principle is derived from summation of forces equals to ma, all right? So then, the first principle will tell us that you can transform all the heat into work, or vice versa, or the work can become heat, no? But is that really correct? We know that in real life, if you look at the efficiency of your car engine, if it's gas, what is the efficiency? Generally, it's about 30% or less, okay? So that means that you're only transforming 30% of the heat into work, okay? Most of it is lost in friction and heat dissipation and everything, okay? So then it was a deficiency on the theory of the first principle of thermodynamics. So then the thermodynamics needed to find a way to define what would be the efficiency of the engine. And that would be pretty easy. The way it's defined is basically, generally, when you want to find if something is efficient, what would you do? You would say, okay, the amount of work divided by the amount of heat will give you the efficiency, no? Let's say you have 100 kilojoules of heat and you only get, and the work of, let's say, of 50 kilojoules, you divide the work divided by whatever you put in the heat will be 50% efficient, no? So that's pretty easy. But the other one is that you know that once you burn the gasoline in your car and you transform it into heat and you make it into work, can you get back the gasoline that you burned from the work? You cannot get it back. So these are another problem of the first principle of thermodynamics is that some chemical reactions or some processes will only occur in one direction, okay? I like to give another example. It's not 100% correct really theoretically, but I think it's a good example for the understanding is that if you have water, you can go back and forth between, let's say, liquid water and ice, no? And you don't lose any quantity of the material, of the substance water, okay? But if you burn a log of wood, you're gonna get ashes, but then from the ashes, you cannot get back the log of wood, no? Okay? So if you want, one, you can look at it as being a process, you can go back and forth, that would be called reversible, and the other one, we only occur in one direction, will be called irreversible, okay? So in order to introduce the term of reversible or irreversible, we'll add a concept, which is the concept of entropy. So in order to get to the second principle, we get the concept of entropy, which is quite complicated to understand, to tell you the truth. But basically, this one will help us to know if a process is reversible. So I'm kind of doing a summary of what we'll be doing in class, or irreversible. So every time I ask in class, what is for you entropy? Do you have a good definition? Over here, I'm not gonna ask you because we are recording everything, but generally the answer that I get is that it's a measure of chaos, okay? That's what I get. I say, okay, and then I say, okay, so what is a measure of chaos? My answer, Johnny, is that when we don't know something, we like to do it complicated so that nobody can understand it, no? Okay? I had actually a friend that studied with me. He never finished, but it's fine. And he ended up finding a job selling electrical components. So when I talk to him once in a while, we eat and ask him, so how is your work? Oh, I'm selling electrical components. And I'm like, how do you sell them? He said, oh, I tell them that the entropy of this one is lower than the one of the other, other company. I say, so what is the entropy? He said, we have no idea, but nobody knows really what it is. Okay? So everybody shakes their hand like they agree. Okay? So I hope that by the end of this class, the definition of entropy really It's not complicated. There is a measure of chaos. Yes, obviously it's a measure of chaos, but that's the complicated definition. The simple definition, the entropy is a measure on how well you are using the energy that you have at hand. So if you have, let's say, 100 kilojoules of energy, and you're able to recover 100 kilojoules of energy at the end, you are making a good usage of your entropy, no? Okay? Because your efficiency is 100%, you are not losing any entropy. In that case, the entropy will be 0, okay? Now, let's say you have 100 kilojoules of entropy, but at the end of a process, let's say you make any process, okay? You compress air, okay? And at the end of the process, you're just gonna get, let's say, 97 kilojoules. So what happened to those 3 kilojoules? You lost those 3 kilojoules in the medium, in the atmosphere, no? Okay? So if you want, the entropy in that case is not 0, will be some type equivalent to that 3 kilojoules that you lost, okay? And now, what do you know about energy? If you look at in this class, or in any closed system, if you increase the energy into the system, what's happening? You have more interaction between the molecules, so you increase the chaotic motion, no? Okay? So it's true that if you increase the entropy of the medium, the more energy you waste within a system is gonna make it more and more chaotic, no? But I think that's a very complicated definition. A simple definition of entropy is a measure on how well you use the energy that you have available, okay? But again, we look at that later on. Okay, so using the first principle and the concept of entropy, then we derive over here what would be the second principle of thermodynamics. Okay, so today I think I'm just going to do like a brief summary, and I will start really with the class on Thursday, so please watch the video. Okay, so this will be mainly the 3 big parts of the class. First, derivation of the first principle of thermodynamics, then we study what is entropy, and then we combine the first principle with entropy, and we derive the second principle of thermodynamics, okay? But in between, there's a problem, because in thermodynamics, we deal with substances, okay? So let's talk about a substance, and I will give the definition next time, but so that the easiest one is always to select water. You have a substance. Now, you can find a substance in different states, okay? Let's see, can I do this bigger? Yeah, helps a little bit. So you can find a substance in different states. So you can find water in what? So you can find water in state, let's say solid. That will be ice. You can find water in state liquid. That would just be liquid water. Or you could find water in state gas, which will be, if you want, steam or vapor. Okay, so here we have the same substance that you can find at 3 different states: solid, liquid, and vapor. So now, how do you differentiate the substance water at solid, liquid, or vapor? So the answer is, do the properties, if you want the density, think about density, heat capacity, but let's just talk about density now. Is the density of water the same for ice, liquid, or vapor? I mean, I think the answer, you might find it many times. If you put a bottle of liquid water full into the freezer, what's gonna happen? It's gonna expand, no? Why does that happen? It's still water. It's because the density of ice is bigger than the density of water. Yeah? So what happened here? It's the same substance. So what happened is that because of the temperature, there is some chemical reaction that changed the molecular structure, okay? And that changed the properties, okay? Density and other ones. So if you want the state of the state of a substance is defined by its properties. And over here, we can just say that a property could be really just think about density in this example, but also pressure, volume are also properties. Okay, pressure, etc. will be properties. Okay, if you think about it, what was the ideal gas relation? PV equal nRT, no? So pressure, volume, and temperature are three properties, no? Okay. So if you want, the state of a substance is defined by its properties. Now we have two types of properties. This is not important to know the name, just important to know that there is a difference. So for example, in this class, if I ask you, what is the total mass of everything contained in this classroom? What do we need to do? We need to start adding the weight of each one, no? We need to start adding the weight of the chairs, of the tables, so on and so on. So basically, in that case, you need to add all the different values of the different components to have the total value of, let's say, the mass in the classroom, no? Now, what happens if I ask you, what is the temperature in the classroom? Are we going to be doing the same thing? No, in this case, it's not going to be the temperature of each one of you added together. But what will you do? You probably might take the temperature at 3 different locations and you will take an average, no? Okay? So one property, if you want, is called extensive, which is the summation of each one of them. And the other one, which is just related to the surrounding, is what is called an intensive property, okay? But if you want, without putting those names, would be one property is summation of, let's say, all parts. Again, we will do some notes on this. Summation of all parts. And the other one will be like a global property. So this will be like mass. Okay. If the other one would be like a global property. And this one would be more like, if you want, temperature. Or pressure. Okay. All right, so here what's important is that you know that this substance is defined in different states. Oh, and that each state is defined by its properties. Okay? Okay. Now, the fact of going from one state to the other, so let's say you go from state 1 to state 2 is called a process, okay? And here you have different type of processes. Let's see if I can find it. Okay, so you have different processes. Let's say you can have a process that will be constant. How do you call a process that will be at constant temperature? Will be an isothermal process, will be constant temperature. Then constant pressure will be isobaric. Constant volume will be also correct. But again, we will look at this again. And one process that has no heat, so this is a T constant, P constant, V constant, and the other one, the last one, is what is called adiabatic process. And this one will mean that there is no heat between one state to the other. Okay, so this is quite important because the way you're going to select to which table you're going to go, it depends on what type of process you have. So for example, if you want, I can do here very quick, a very figure. Oh, sorry for that. Yeah. What happens is I zoom in and I forgot. Yeah, sorry for that, guys. Let me know. So over here, this is important. You will see one figure that we'll do probably in 2 weeks. So you don't need to know it by now, but if you want, I can do it here. Let's say I do this will be temperature, and this will be volume, okay? The TV. Again, I know you're not gonna remember this, but the temperature is what? Is a global property, which is called an intensive property, okay? Temperature of the room. Now, what would be the volume of the room? Would be, if you break this into letters squared, would be the summation of all of the letters squared, no? Or cube. And this property will be extensive, no? So if you want to know which table you're going to use, you're always going to need to know one intensive property and one intensive property. So in this figure, for example, for water, all right, let's say at atmospheric pressure. Let's see how the pressure cooker works, okay? So atmospheric pressure, let's say you're boiling water on your pot. Okay, so this process happening at constant pressure, no? The pressure will be 1 atmosphere, okay? So as you increase the temperature, the water will start boiling. So this is here on the left-hand side of this curve will be the liquid state. Now, what happens once you get to the boiling temperature? So this temperature will be what? This boiling temperature will be about 100 degrees Celsius, no? Now what's going to happen to the water in the pot? This is still happening at constant pressure, but now what's going to happen? Some of the water is going to remain liquid, some of the water is going to become gas, correct? So this part would be liquid, this part would be called a mixture. And now, as you heat the water, the more you heat it, the more water is going to be transformed from liquid to gas. So if you think about it, this point here will be saturated liquid, everything will be liquid. And this point, what will happen here, everything will be gas, no? Okay, so you come here, this is the gas. And now the right-hand side, so if you want, this is liquid over here. This will be a mixture. So this figure, don't worry, you're going to be using it a lot. And this will be gas. So now if you have gas, if you keep heating the gas, it's just going to increase the temperature. But if you look at this line over here, this is a line of constant temperature. So this is a line of constant pressure, sorry, okay? And this pressure will be 1 atmosphere. So you put water boiling, initially what's gonna happen? You increase the temperature, okay? Once you get to 100 degrees, it's boiling temperature, some of the water is gonna become gas, some of the water is gonna remain liquid. At this point here, everything will be gas. And now it will just be increasing the temperature of the gas, okay? All right. So 2 more things, and maybe I stop, and I will stop, or 1 more thing. Not sure we have time. So this is very important, guys, if you are AE students. AE curriculum is spectacular, it's really good, but like everything, there is some weaknesses in everything, no? Nothing is perfect, okay? So I think one weakness or 2 weaknesses of the aerospace curriculum is that they are missing a class called heat transfer. Let me write it better. So heat transfer. Okay, so this is not something that is really part of thermodynamics, but it's important. Because thermodynamics, when you move from one state to the other, it doesn't matter how you move from one state to the other. It doesn't matter how you apply the heat, how you apply the pressure or anything, no? The only thing that matters is to know what is the value at the end results. So in other words, if you're going to transform liquid water into gas, thermodynamics do not care about how you apply the heat. Okay? The only thing it cares is that, okay, at state 1, my water was liquid. At state 2, let's say I had 30% of liquid water and 70% of gas, no? But the way you apply the heat in order to boil the water is completely irrelevant, okay? This class of heat transfer is giving you an insight about the different methods that you have to heat the water, okay? And we do a little bit, okay, in this class, but really just the fundamentals. So there's 3 different ways of transferring heat. One is conduction, which basically is what you have in most electric stove. You heat a wire, no? And the wire heats up through the medium, and then you put a pot on top of the glass. The heat goes through the glass, and the glass will heat the steel, and the steel will heat the water, no? Of whatever is inside. So this will be the conduction. Now, the second one is convection. So what do they call a convection oven? It's still a conduction oven, but what is the only difference? They put a fan into it, no? So now what happened? Because of the fan, you circulate the heat, okay, inside the oven. So increase the velocity of cooking, okay? So convection, for example, is that if you have a fan in your room, what is the function of the fan? Is to increase the velocity of the air so that you can cool yourself faster, no? By moving the medium. But now I'm gonna have something that you may have never thought about it. Is on the long term, is the fan cooling or heating your bedroom? On the long term, the fan will be heating your bedroom. Because really, what do you have? The blades are having friction with the molecules of air. Friction generates heat, no? If you want, the little engine inside the fan will be generating heat, okay? But obviously, the amount of heat it generates is not as much as the sense of comfort that you feel because of the increased air that increases the convection. It's like if you go to the beach with no wind, you are extremely hot, but if there's a little breeze, you feel cooler, no? But it's still the same temperature. Temperature has not changed. It's just that you are able to remove the heat from your body faster when you have convection, okay? And then the last one is what? Radiation. So radiation, the easiest example is that you know that heat from the sun travels through space and hits the earth, no? So the main difference between these 3 is what? Is that the radiation requires no medium, and I will finish it with this, no medium. You can go through the vacuum, no? It's like a wave. Convection deals with what? If you want with liquid or air mediums. So basically it's a substance that can move. And conduction will deal with what? With solid mediums or solid materials. For example, you will try to conduct through copper, steel, aluminum, no? Different materials. So we do a little bit of this. Actually, this is at the beginning of the semester. All right, so I'll stop over here and I will upload these videos. I will put them together and I will upload them, okay? And Thursday, I know you will not be here, but I will start really with the class. All right, guys, so let me terminate this. Stop recording.